And with that, ladies and gentlemen, we'll kick off the GYSS 2023 with this morning's opening plenary, Exoplanet Revolution, Exploring the Consequence of a Paradigm Shift by Professor Didier Queloz, winner of the 2019 Nobel Prize in Physics. The Q&A session will be moderated by Professor Tan Ming Chuan. Professor Queloz, please.
Thank you. Thank you very much. Should I press? Oh, great. Okay, so, well, at first I must say it's a real pleasure for me to be here. I have been attending GYSS in the last 2 years, but I was in front of my computer. So it's not the same vibe and feeling to be interacting with you here. It's clearly see this energy in the audience that was mentioned before, and that's fantastic. So what I would like to share with you is a topic which is well known, but I want to also drive you to when there is a big discovery such as detecting planet on another star, there is a lot of, how to call that, unexpected consequences that is driving to even further ideas and further programs. And that's a bit what I want to explain to you. So it may give you some idea how science works if you're not familiar. It may also give you an insight when you touch and you get lucky to be very close to something extraordinarily big and how much your brain has to adjust to the consequences of what you're dealing with. This is the idea of the consequences paradigm shift that we're talking about. Okay, so let's start with a simple picture, in a way, is where we are in terms of solar system. So I tried to get for you the latest updated understanding of the solar system in one picture. So this is how it looks like. This is anything that we know in the solar system. Well, you have the planet, of course, but there's a lot of other stuff you see which has been identified. I don't think we have just added all the tiny bits, but when you look at the solar system, it's pretty clear that it's a very complex system. Well, if you think about that right now, it took us about 5,000 years to build up that understanding. By bits. The solar system happened to be, as a topic, a fantastic lab that actually used for math, to test math and to try to test the functioning of planets. And for a long time, we can even say that the foundation of the science, the modern science, has been tested very early on in the 15th century on the solar system. So this is where we are right now. We have this very complex picture of the solar system. And of course, having so much information on the system, being able to send probes to some of these planets and also some of the asteroids and bringing something back, gave some sense of confidence that we understand the solar system. Well, we have been working on it for a long time. We have a pretty good predicted power. We can predict where the moon will be in 1,000 years. We can predict a lot of the location of the planet. We understand quite well most of the planet. So this is kind of the background where we are. Now, when you think about this as a system, obviously, you are dealing with extrapolation. So how do you do to extrapolate from that, which you understand pretty well, assuming that a star like the sun is just a star, and there are plenty of other stars around. Even staying in our galaxy, you're dealing with more than 1,000 billion stars in the galaxy. So what about this on the other star? It's also a very old question, but that's an extremely difficult question to answer, and it took us a long time to start this. So this is what we call exoplanet sciences. So in 5,000 years, we have built up the understanding of the solar system, and what has happened in the next 30 years, we have deconstructed a little bit the story, which is quite fascinating because how far could you understand something so well, but as soon as you see this from another perspective, you deconstruct it And I think this is really the heart of the scientific process and how the system works, and how much we should be aware and alert. And there is plenty of things like that. In my field of physics, you may have heard about dark matter, dark energy. It's a bit the same stuff. I mean, we don't understand it, and it's pretty clear that one day we will understand this, and we have to deconstruct a little bit what we understand about the matter as it is today. And that happens in other fields certainly as well. So this whole idea that when you form a star, you form planet is rock solid concept in astrophysics. And this is about the story, how it works. You have a lot of material around. This material is created at the beginning of the universe. It's the hydrogen, there's plenty. It's a very boring moment because there's not much stars, and at some point stars start to pop up. This is the reason why a fantastic telescope called the James Webb Space Telescope right now is flying and operating, is trying to find out this first generation of star that kick-started the formation of the galaxies and the structure of the universe that we see right now. But on each of these stars, when you start making the star, because you essentially you collapse the material that you have around, which is hydrogen. It's the most simple atom you can think about. There's a couple of laws of physics, very simple. One of them is called conservation law, which you have to conserve the angular momentum. We start rotating, you cannot really stop. You have to just rotate or faster if you shrink, or you have to expand and to slow down. So very naturally, the rotation pattern, which is completely random, gives you a specific direction, which is the axis of the rotation and the rest. On this simple fact, you create a structure which is called as a disk. So this idea is pretty old. It has about 300 years old, and it follows directly the Newton law. And the idea that when you form a star, you will form something like a disk, connects with the structure of the solar system. So on that premises, you can bring the dots together and you say, okay, well, this is how the planet forms. You create a star, you create a disk, and the planet form, and that's how we understand the solar system. And actually, this is the output of this. So you would expect to have a planet or planetary system on any star, according to this scenario. And that was a bit how the astrophysics reached the 80s, with a good understanding of the solar system, with even a prediction saying, well, we have a good understanding of the solar system with a giant planet like Jupiter farther out, and a smaller rocky planet inside. This is because of that process. So I don't want to talk too much about that. I did last time to explain practically what is the physics behind this idea. So all the planets should look in a similar way to the solar system. We must have plenty of rocky planet, similar to the Earth, within this kind of regime of period of distance, and further out, plenty of giant planet. Well, and then this is where start the fun in science, is everybody was looking at this, including us and myself at the beginning, but it's not at all what we found. In a way, that was a piece of luck. The fact that we didn't really exactly found what we expected, because what we found is even more interesting. So what has happened essentially in this, when you start looking at planet and the way we understand the planet, and you may have maybe checked the count, I think we know more than 5,000 planets right now on other stars. There will be even more. What you have as a single picture is, oh sorry, before I want to show you something before we talk about the planet, I want to show you that this is one of these latest picture that we collect from stars with planet being formed. It's being done with the ALMA system, which is millimetric array in Atacama Desert. And the idea that you have disk where you form planet is quite common. It's something that was pretty obvious. And this is one of these collections that we have right now. This is just a couple of years old right now. So the idea you have stars and you have disk and you have planet is pretty common in there. So when you start looking at planet, you expect to have this solar system picture. But actually, this is not what you ended up at the end. This is a summary of all the known planets that we have just a couple of months ago. So every point in this diagram, which is organized in period mass or period size radius of the planet, corresponds to one detection of a planet. We detect the mass using the fact that an orbiting planet is moving a little bit the star, just by the center of gravity of the star. It's a global balancing. It's called center of gravity there is a reference, and you have the star orbiting the center of gravity of the system. You detect that by measuring the radial velocity or the speed of the star. You get the mass. You detect the size of the planet if you get lucky, and the planet is just crossing the line of sight between you and the star. And they create, for a brief moment, a kind of a small decrease of the light of the star, and you get the size, the radius here. And this is the period you have here. So every point is a planet. So the first one that was picked was the planet orbiting 51.b. That was in this very awkward configuration, about 4 days and about 300 times the mass of Jupiter, so the mass of the Earth, which is about one the mass of Jupiter, which is here. So we detect the first planet in this area, and you see there is plenty of others right now that have also a short period and a mass which is of the other of the mass of Jupiter. It's more 300 times the mass. Jupiter is here. You see the Jupiter here. So the fact we picked the planet at that locations here in period and not at that location here was a very dramatic moment. It's a very stressful moment because for a couple of years, essentially no one believed us because it was so awkward and didn't make any sense. How could you build up a planet like Jupiter so close? Well, it took us some time to realize that actually the mechanism of the formation of a planet is way more complicated than it looks. And you can well make a planet in that location, but it doesn't mean that the planet will stay. That there's a lot of physics going on when you form the system, including the interaction with the disk, that can move in or out the planet from its original orbit. So that was the first big surprise that happened here. Now, the second surprise is by improving the technology to detect planets, essentially by flying a satellite called Kepler, a whole new, we'll call that, populations of planets popped up. When I say whole new, it's because a lot of these planets you see on this diagram, they have not a single counterpart in the solar system. The planet in the solar system are here, the Sun the Earth and Venus and Jupiter. So they all look to be much closer to anything we know. Essentially, most of the planets we have found and we have identified, they would fit in within the orbit of Mercury. Okay, now the interesting bit of that is how come? How come we ended up in these situations? So to get the picture really complete, I have to add a bit of information on this diagram. The first one is I have to add this. This is what I call the boundary of the technology that we're using in terms of the planet we can detect. So anything on the left of these dotted lines is something within reach of the technology that we're using today and we have used in the past. Anything on the right is out of reach. We're working on that right now, but so far it's really challenging, out of reach. So you really start to understand something here, is the fact we've picked up all these planets, well, first is because we had the capability to find it, similarly to this diagram here. But having the capability to find something is not enough if this data just doesn't exist. And actually, the piece of luck or the gift of nature, they exist. So all these planet populations, no one would have predicted that. There is not a single paper in the literature about the possibility that the planetary system can be dramatically different from the solar system. And you see, it's quite interesting when you think about that, because 5,000 years of study on the solar system an exquisite understanding of the solar system, and we were blind, completely blind to the whole picture, because we never looked at the whole picture. We were obsessed by the small picture. And that's valid for many kind of different topic of sciences. If you can explore and look for the big picture or challenge the accepted knowledge, do it, because it's very likely that they may be surprised. And that's one of them. Now, what is fascinating here is on one way, we picked up something that we were not expecting, but also we failed at detecting what we were looking for, almost. Well, especially here, I think the Kepler mission were obsessed to find Earth-like planet. Well, they did find Earth-sized planet, clearly, but in a very short period, a couple of days, but never really an equivalent to the Earth. The term of the mass is a bit more confused because we still fail on this, but we got some kind of Jupiter planet. You see there is Jupiter here, so there's a couple of Jupiter planets. So in a way it's reassuring. There are some planets that may be looking like our own Jupiter at the distance of Jupiter, but we still have quite a massive population here that doesn't fit in at all. So this is the kind of a first, I think, learning experience. I call that also a gift because without these populations, I may unlikely be talking to you right now. It means the field will be dormant, we will have very few discoveries, and we were struggling battling to find the few planet that is actually a kind of a copycat of the solar system. So the fact we have all this planet created what we used to call a revolution. But revolution in a global sense, because it opened us a new perspective. And I want to try to explain to you what are those perspectives here. Of course, you see what I'm leaning on. I'm leaning on the question of life in the universe here. And now you have to understand how this is going to be connected here. Okay, what we can do right now, you see there is two colors, blue and red here. And this is to identify the techniques that's been used to make the discovery. So there is some red in the blue and blue in the red. It means in some of the case, the planet has been observed and detected both ways. We have the mass and the size at the same time. So this is an interesting move. This is something that started about 5 years after the first discovery. We start doing what's called astrophysics of planet, or if you want, geophysics of the planet, if you're talking about planet that would be more like a rocky planet. Before we go into the detail of the structure of the planet, it's nice to have an idea. What is the likelihood each of these block or categories of planet happens or appears or detected on stars? And we have this amazing number that few percent clearly are like this extreme 51 peg-like story, what we call the hot Jupiter. They're kind of a rare, the weirdos planet. We have 10 to 20% of planet that looks like Jupiter, our own Jupiter, but we have more than 50 to 80% of the star that happen to have a planet of that kind. So what nature is telling us here is whatever we believe we understood the formation of the solar system is just one amongst many. And it's certainly not the dominant structure of a planetary system in the universe. We are not the most dominant structure. We are on the corner side. How rare we are, it's difficult to know because we have not been able to explore that element here yet. But certainly there is a huge amount of planets that are way closer to the stars than us in terms of regime here with a size between the Earth size, maybe 2 times the size of the Earth, which has the consequences. It's very hot on this planet because they're very close. So most of these planets are extremely hot. We even talk about lava planet on some of them here. We're talking about the hot Jupiter, dealing with this one, and the more you move down here, you talk all with hot Neptunes and hot super Earth. That's kind of terminology we are using here. Now, when you bring them together, all this planet there, you can build up that diagram. which is an amazing diagram when you think about this. When you bring the mass on the size of the planet, it gives you the access to the density, or more like a bulk density of the planet. All these data points are real data. It's just not theory. This is observations. It's observation done with a lot of high-tech technology by many teams in the world. It's really global effort here to reach that. The word global was used, and I would like to just say it again. Science is global, and this is a global effort all over the world to produce this. What you do see, you recognize Jupiter here to help you a little bit, Neptune here, and Saturn here. And to read this diagram, there's a lot of dots here, and there's what's called error bars. This is to define how far we're going to be off. So 1 sigma error bar, if you want to know the full story here. There is a kind of a structure in this diagram that tell you about the density. And to read this, I added known density structure. So one you can pick is the one of Jupiter, our own Jupiter. So you can take the density diagram of Jupiter, and once you know the structure of the physics, the pressure, the temperature profile you have, you can remove or add material into Jupiter. It will change the size. It doesn't change that dramatically. The reason why, because of the pressure is such that you don't behave like a gas, you behave more like a metallic structure. It's completely, the word was mentioned, quantum mechanics, so it's completely driven by quantum mechanics. This is why it's flat here. You can add and add and add and mass. It's not going to change the size. And it's a bit like you have a random people running around, and then you bring the people into a room like that. You're very organized like a quantum system. Right now, everybody is seated. This is exactly how it works. As soon as everybody starts to stand up and go everywhere, we will need more room, more space. Otherwise, we'll be bumping each other. So this is when you get the gas and you get bigger. This is the story why you can have more and more people. And the more you get organized, the more you can pack people together. So the system here predicts pretty well the density of Jupiter and Saturn. Most of the Jupiter planet that we have found, they're slightly above this diagram. Some of them quite a lot. It means they are lighter. The density is more fluffy. And it's very likely because they're hot. So you have to imagine most of the Jupiter, they're hot. They have a high temperature on the outside, so they don't really strictly follow the structure of Jupiter. The exact understanding what's going on it's not understood, but there's certainly something in the nature, the physics of the upper part of the planet that is modified. And you can get a Jupiter mass object but then with the size about 2 times, this log scale is 2 times larger than Jupiter. Remember, it goes to the cube, and if you have to account for the density. Now, when you go down this line, you reach the mass here of Neptune. So you clearly understand that the structure of Jupiter doesn't produce Neptune. And for good reason, because Neptune is quite often seen as a failed giant planet. In a sense, when you have the build-up of the planet reaches a maximum size at a time when there is no more material around that you can grab and keep the growth of the planet. No more food for the planet to be built, and that the food missing in Neptune is the hydrogen, because the difference between this and that is there is way more hydrogen into Saturn and Jupiter. So this is why you grow bigger. Neptune never reached that. There's a little bit. It's much more denser. This is why it's sitting here. So there is this kind of artificial planet that we call a water planet. So if you use water as an element, you make a planet with that. You cannot really make only a planet of water, but to give you an example, water is quite used because it's well understood. Water on a very high pressure, very high temperature has been studied essentially thanks to the work of our scientists, because water is inside the earth everywhere, and they need to understand the pattern of water to study the earth. And you can make a planet entirely to water. It would be a very weird planet because the core would be kind of icy hot water, and we have a huge oceans and with different densities, so it would be quite awkward. But that's what it would be, and you clearly see there are planets sitting in this regime. We have no idea how they are exactly, but we know that they may be water world in a sense, or maybe a mixture of everything. What we know is the planet like the Earth, a rocky planet, essentially made of rocks, silicates, would be sitting along this green line, one Earth mass, one Earth radius here. And we do have planet detected within this regime. So what is fascinating on this diagram is, as of today, we have planets that we guess may look like the Earth in terms of density. We also have planets we have a mass which is not far from the mass of the Earth. Let's take 3 times the mass of the Earth here, that have a complete different structure. You can move up here, and even some with extremely fluffy. So the simplest idea, when you get a small planet, you get something like the Earth, is not true. In the process of making the planet, you can end up with a different structure depending on the history that is making this planet. And that's a bit where we are already right now. And it's expanding the concept of how it corresponds with a given mass or given structure into what the planet is exactly. Of course, it opens plenty of questions. If it's not exactly like the Earth, how does it look like? And that's a very good question, actually, to find out this. So to move forwards on this, we can do more than just getting the mass and the size of the planet. Well, the reason why is the fact there are a substantial number of planets on a short period increase the chance of this configuration, which is called a transit. If the planet is close, if you just look at the system the right way, you may be just at the right angle where between you or your machine and the star, the planet is crossing the line of sight. And it creates for a brief moment a signal. Actually, there is 2 signals that you can use. The one where the planet is in front, that we used to call a transit in astronomy, and the one when the planet is behind, that we used to call an eclipse. These are 2 very specific moments, and we are using these 2 moments in a very intensive way right now. And I would like to go a little bit in more detail, because most of the publication you are seeing these days, and you will see in the next 20 years, will be about that. The reason why is because we are building, or we have built, and we are operating, I say we, the astrophysical community, the biggest equipment in the world right now to do that. One of them is the James Webb Space Telescope. It's doing exactly that. The other one is one of these telescopes. One is in Chile. It's the biggest one. It's the ELT built in ESO. There is another gigantic telescope also being built by our American colleagues in Hawaii. So this is really the purpose of this. So how does it work? Well, the principle is pretty simple here. What you do is you have to imagine a transit. So here we are in the GYSS. We're looking at the Earth, right? Behind there is the moon. It's like the Earth transiting the moon that we do see here, right? So let's imagine you have this transit. What I want you to focus on is this tiny, tiny layer here. This is the 10 kilometers that make us alive right now. It's a biosphere. It's 10 kilometers max. Well, I would not advise to go to 10 kilometers. I would still stay below 6,000 meters. That's okay. After it becomes really dangerous. But that's a bit us. And it's a bit bluish because it's a Rayleigh scattering. It's the blue is diffuse, the red just go front. That's what we know what the sun said. Well, if I take the very same picture at the very same moment with another wavelength, so I look with another color, I go in the infrared, which is something the spy satellite love to do, they don't see the atmosphere anymore. They just see the surface of the planet, which is the purpose of this satellite. So have a look at this exactly in detail, and this is moving in the red. You've seen the distance here has changed a little bit, so the planet looks smaller, actually. When you look in the same event, the same planet, in the red. Actually, this one is 8 micron here. So I can pick up my color, my wavelength, differently, and I can be a little bit of a trick. I go slightly more in the red, in a wavelength which is sensitive to molecules, which is an essential molecule for us, which is ozone, because ozone is protecting us from the UV radiations that would essentially destroy the DNA if you're just left without the ozone. So this is now a picture with a wavelength that is sensitive to the ozone and reacting to the ozone is there. It's bigger, 50 kilometers. So you've seen here the change into the atmosphere. So what I'm trying to tell you here is, depending on the color you're looking at a planet in the transit event, because the transit is detecting a size, you're seeing a planet with a different size, essentially. And this size can be then transformed into a composition of the atmosphere of the planet, following the same idea. And you may have seen this picture from the James Webb Space Telescope some time ago, which is one of the very first pictures, when they look at a transit at different wavelength, color. This is the wavelength, visible, and this is the infrared. And here, amount of light blocked. So it gives you essentially the size of the planet. So the planet has a different size depending on the wavelength you're looking at it. And you get this ups and downs, ups and troughs, you get all this, and then you can then work backwards on that and trying to fit in what is the structure of the atmosphere that is matching that observations of the change of the size of the planet according to the color. This is how we can tell you what is the composition of a planet without going there. Even if the planet is 50 or 60, 100 light years away, if the planet is transiting, this is how we're doing it. With this kind of machinery we can have access to. And that is open a complete new windows. So when you think about that, I mean, we're talking about planet on another star, we're talking about planet, we can get the mass, we can get the size, planet like the Earth possibly, rocky planet, planet for which we can observe the atmosphere of the planet. Wow, this is quite amazing what can be done. And this has happened in 30 years. So 5,000 years to build up the understanding of the solar system. And it's amazing acceleration right now of trying to fit it in, how the solar system can be compared with all these different systems. Now, we can do more than that, because when you look at the system in transit, actually you look at the light, the combined light from the planet and the star together. Well, with the exceptions when the planet is behind in the eclipse. So if you use a telescope, you point to a planetary system in transit, you record the light, it's called the flux here, and you have this kind of structure. So when the planet goes in transit, you lose a bit of light, it creates this decrease, a fraction. On the big planet, it can be done on the ground. That's why a lot of this transit has been detected on the ground. A small planet has to go in space, because space gives you the exquisite accuracy you need to do that. And then there is a moment when the planet is behind, that we call the eclipse. So let's think about that. There is just a zoom here, and this is the time. This is actually the moment when you get this eclipse moment, when the planet is behind. So it means anything up to that point filling your detector with light comes from the star, only because the planet is behind, right? So anything which is above that red line is the light from the planet. So you don't need to see the planet to see it. You just need to find out how to remove the star. And that's exactly the same problem when you want to get the direct imaging. The challenge, if you want to make a direct picture, is to remove the star. Right now, it's easier to use the system and to remove the star like that than to remove physically the star from an image. It will change, because there is a brand new technology being designed. This is based on combining different techniques together to remove the extremely high light that blur you from the star to see the planet around. We have a couple of systems for which we have seen it, but most of them we don't see them. We don't need to see them to know. And that's what is magical. When you think of the limitation we have in terms of what we can capture and how much power the brain and the imaginations are given to us, we can tell you what is inside an atom. We can tell you about quark. We can tell you about boson. We can talk about something which is a virus we don't see. We used to use machinery to do that. We can really make a picture, a mental picture about this, We don't see it with our eyes, but the brain and the machinery we have built is so powerful that we can get into the information, and they are real. So it extends, and the scientific knowledge, for me it's fascinating, extends so much our capabilities to see the world, and the complexity of the world and how it is. This is exactly how then we see the planet. When you do that, well, you then definitely see what we call the dark side of the planet, where there's not less light, it's darkish. At that moment, the planet is showing you the dark side. At that moment, you see the bright side just before the planet goes behind, because part of the light is hitting from the star, the planet, maybe reflecting or maybe shining just by natural thermal. Depending on the wavelength, again, you see the reflection, or like the moon, or you see the shining effect. But that's what we can do. So with all of this, we're getting a pretty decent picture of the atmosphere of a planet, of the temperature of a planet, whether a planet has an atmosphere or not, whether a planet has clouds, what is the nature of this cloud, and if there is no atmosphere, even we can say something about the nature of the ground. What is the ground made of? You can imagine if the planet is made of water or a certain type of rocks, is not going to look the same. And we know all that. If you go around, you see some rocks are red or a little bit greenish, or the water has a different pattern as well. So all this technically, potentially can be seen. It's just a matter of time, picking up the right object, having the right equipment, but you don't break any law of physics by getting at that level of information here. Now, I move to the next stage. When you think about that, and this comes, I think, the breakthrough, all that. When we started to detect planet and detecting atmosphere of planet, of course, the question about life on this planet started to become proeminent. It's not an easy question, because you can ask the question exactly how do you detect life, how do you find life, how do you do that? But if you start in a simple way, in the same way we've started at the beginning, you can start from what the only life we know about, which is life on the Earth right now, and ask yourself, okay, so let's look at Earth, let's look what is visible on Earth, and how far we can see something on the other planet. Well, what has been talking about quite substantially in the past is the fact that there is a specific atmosphere in the Earth, you have here, with specific molecules. And you can argue that some of these molecules may not be there without life. And it's clearly true for the oxygen in combinations with the nitrogen you have here. You can produce elements similar on the planet, and I give you some examples. It's one of my colleagues, Vicky Meadows, that produced this, demonstrating you can have water, you can have oxygen, also depending exactly of the nature of the rocks and the amount of energy that can break the molecules from the star, and you can have quite a high diversity of atmosphere. Now just think about Venus, the way it is, and how much Venus is different in terms of atmosphere from the Earth, while the planet Venus looks very similar, same mass, same size, very similar, like a twin to us. So we start entering into a very fascinating moment, because in one way we have the Earth as a reference, but we can see that soon we will have hundreds of rocky planet atmosphere recorded and being observed. What we're going to find, I don't know. But we're going to see things that we have never imagined. And maybe the kind of atmosphere that we have on Earth is very rare. And that would be an interesting moment. And I keep telling that this rise of oxygen that happened 2 billion years ago due to life, what's called the great oxygenations on Earth, makes us very special. In a way, when I keep being asked whether we have to be careful not to signal to an alien civilization, I keep telling everybody, well, I think, come on, we are visible since 2 billion years, because the great oxygenations make us very visible as something is alive on this planet, because there's too many oxygen on this planet, clearly to be explained other way. So we should not be worried about this, because we are well known since 2 billion years, so nobody came that far. Or maybe they came and we don't see them. That's also a possibility. But the idea of the atmosphere as a proxy is something that is not just a sci-fi idea. it is something that we can do, and we will be doing, and we will try to explore and to push this and to see how we go. Now, what I would like to introduce here, we'll do way more than that, because the beauty of astrophysics, I keep saying this is the best lab everybody could have imagined. The only difference is don't touch. But you have the time, we have amazing pressure, density, we have plenty of parameters we can play. Certainly, this is the only lab we can play with the time. So this is how we believe would look the Earth, where we are right now, early on, about at the time when life started. So what I want to show you that is the way you initiate life on Earth is a very different planet than the planet where we know where life is everywhere on Earth. Maybe if you would to erase entirely life on Earth, that would be very difficult still, I think. Let's imagine. Maybe the condition to start it will not be met again. So the idea that the situation right now is good for life, yeah, it is, because life made it in a way. But this is the moment when everything started. And we know about what was happened at that time. We know what is around, CO2, nitrogen, we have the volcanic activity, a lot of infall from comet, maybe a lot of cyanuric acid, HCN falling in, a lot of stuff, very interesting stuff. And this moment is the key moment for understanding origin of life on Earth. The problem is everything is gone forever because there is not a single trace of that. And life as we see it today is the output of a long process of evolutions. What is the element from the very origin that you have into life right now? So you can argue possibly the amino acids, something like that, but how far can we really connect to the simplest form, simplest element of life? It's very difficult to answer these questions. Well, the good news is we have planets that we can observe that are in the exact state right now, because some of them are maintained in that state. We call that the lava planet. We call it all these planets that are too close. They are rocky, but they're too close to be like the Earth. But they certainly are like the Earth at the very origin of the Earth. So you see where I'm trying to tell you right now. I'm trying to show you that the fact we have this diversity of planets is maybe an opportunity for us to use the universe as a lab. It's like playing with the parameter of the Earth. Let's change the parameter of the Earth. Let's go back in time. Let's see how it looks like at the time when the temperature was different. It was much more lava planet, much more volcanic activity, much more infall, and so on and so on. And then see what we get. What kind of atmosphere do you get? Could you compare these different planets? Could you learn something about the nature of this planet? Could you understand something about the exact compositions of the structure of this planet? And that can be done. It can be done, but just don't touch. Just observe and look at as many stars you can do. Well, the good news is there is more than 1,000 billion stars in the galaxy. Well, we're not going to do the 1,000 billion stars, but there is plenty of stars, and it happens to have plenty of planets as well. Because this is one thing to remember about planet discoveries of the past years, is there's clearly planet on any stars. The question is only what the planet looks like. And that is just a matter of time to explore all these systems. So that's a very interesting moment when we're going to push and we're going to make progress. Now, in a global scale, we're going to do something which is getting closer to what Earth scientists are doing. So Earth scientists are quite familiar with this kind of picture, which is the way to express how the Earth has evolved in the past 4.5 billion years. So you start here, it's like a bit of a clock, starting here, and you go around until you're here. So there's various phases on the history of the Earth with very different chemistry and physics going on. The beginning, which is much closer to an astrophysical beginning when you assemble the planet. And it's a very key moment because you get what you get. you end up as Mars, that would be assembling a planet too small to maintain the atmosphere just by gravity, or not having the right element. You have the moment where then you lose substantial amount of what is in the planet, like the light gas, hydrogen and helium, and they're gone. There's a moment when you receive a lot of stuff, CO2. We know a lot of carbon comes on the planet. It's very critical for life. We have plenty of carbon on this planet. And this is coming from outside because there's a lot of CO2 falling from the comet at that time. So a lot of stuff is going on. We expect to have extremely CH-rich atmosphere at that moment. There's some element on that. And then you kind of cool down the planet. You end up with an atmosphere of CO2, full of CO2. And thanks to the volcanic activity, the recycling activity, the balance between the CO2 level and the other gas start to get started. And then at some moment, you have here the beginning of life, so the prebiotic, the condition that enable life. And this is completely changing. Essentially, a lot of the gas we have been processed by life right now. The oxygen that we're breathing right now have been processed by life. And that's not being processed by a star. That's really how it works here. So how do you do all that? How do you make a sense of that? The problem is anything below that level is gone. But you have planets that you can relate to a different stage. We can predict specifically each of this different stage with how the atmosphere would look like from an astrophysics perspective. We create this kind of spectra, reflection spectra at different stage, the Archean Earth before life, the Proterozoic Earth when you start having life here, and then the modern Earth like that. You see that the structure of the atmosphere is very different. You have a lot of water, oxygen, CO2 here, and then a lot of different kind of element at that stage early on. So the hope here, we are going to do that, and I hope I convince you that we can do that with the technique I was describing on plenty of planets. And we may start bringing this story in a more global story in terms of what the Earth is fitting in. So this is really the beginning. This is the beginning of the early discovery process, and we are, if you think about the 5,000 years of history of the solar system, we are the early stage of that moment, but moving to all the other planets in the universe and trying to understand what exactly has happened, how far can we demonstrate that there has been a change of the atmosphere and change of the element related to some organic activity, or whether the condition were kind of closer to the conditions of the early conditions that we had on Earth. Of course, there are some people very optimistic. I belong to that the technology would improve, and one day we should be able to make such a picture. This is the Earth seen by one, remember when the Pioneer missions look back and produce these pictures, the blue dot picture here, famously popularized by Carl Sagan. One day we should be able to do exactly that, but on another star, because we're building the equipment to do this. The day when we can do that, it's just a dot, it's nothing else, but this time with another planet, another star, we should be able to study that dot in great detail and hopefully obtain that kind of information. And the instruments of the future generations are being built right now. They're being thought. We talk about a moon base. We talk about a next generation of big telescope. We talk about assembling big telescope in space done by robots. All this is being thought through because there's a lot of fascinating technology that's being available. So I cannot predict a time scale, but I can make sure that it is going to happen. The only challenge I do see right now is us as a civilizations. Are we going to be wise enough to keep building a knowledge, to reach the technology, to give us the time to do it? And I think this is certainly a big challenge for the new generation here in this audience. I will stop here. Thank you very much.
Thank you, Professor Queloz. It looks like we can also expect to uncover extraterrestrial life in the near future. Right, I'd like to invite you to please take the seat for the plenary discussion. And at this point, I'd also like to invite Professor Tan Ming Chuan, who will facilitate the Q&A. Professor Tan, please.
Thank you. Thank you.
Thank you very much for the very nice talk. I've learned many things myself. I'm also a physicist, high energy theorist, and I agree with your viewpoint that the universe is our lab, and that astrophysics is the way to go to verify many of our high energy theories. Because on Earth itself, we don't have at present some technologies that can reach the energies that we wish to see to probe the smaller elements of matter. But if you look into the stars, into the sky, into the universe, you can actually do that. So I'm really looking forward to seeing what new developments we can have in this area, and I've learned many things today myself. Okay, so I guess we shall go through the questions. We have quite a lot of questions. We can't possibly answer all. We would like to have a mix. Some questions that are online, and some questions they can ask on-site. So please feel free to ask questions on site. I always tell my students this, no question is a bad question, because it is in asking anything that you've discovered something. Okay, so please feel free to ask questions on site if you wish. All right, so the first question that we have. Okay. Okay, right. Okay. So first question, what do you think could be the key enabler technology for the next paradigm shift in exoplanet study?
Well, I think the long-term future is in the space, and for the reason that the main emission of a planet like the Earth is in the infrared, and you don't reach the infrared on the ground. You really have to go to space for that. So any space development that will enable, any technology that enable to do that, and we're considering right now combining telescopes together in space, maybe building equipment in space. The challenge in space is fighting the gravity to lift off from the Earth. So there's a limit in size what you could do. But if you do send smaller bits and assemble them, or maybe build them on the moon, that would be just a massive development. So I'm a great promoter of the idea of using the moon as a scientific element, as a basis for further development, or hoping that the robotic assembly mechanism, we have the robot are doing amazing stuff, but I think what they could do the best is replacing the astronaut really, and doing systematically in a very cheap and safe way, because it's not human, it's robot. And bigger infrastructure into space. So I think this is really the future. It's in space.
Okay. All right, so the next question that we have. Okay. So there was this slide of the planet's distribution. Okay. And I think there was a sort of a dotted line that we say we cannot detect some region. This question is saying that we cannot detect Earth-like and Jupiter-like rather than it is not existing. So I think you mentioned that it's just that we can't detect it, doesn't mean it's not there. So it still might exist, just that our technology is not able to detect that region with large periods.
Yes.
And small masses.
So I want to make clear, I think the reason why we have not detected an Earth twin doesn't mean they don't exist. And I can tell you it's a bit of an obsession for me, so I'm part of a big I'm leading a big consortium, right, to try to fix that problem. I think we have been too optimistic in a way, and then we have to go back to the blackboard, and there's certainly challenges, like all these techniques of discovery of planet rely on how far we can rely on the star, because the star is a reference. We use the star as a proxy for the transiting event, or as a proxy to compute the radial velocity. But the star cannot be trusted at the level we're looking at, so we have to work a bit more on the stellar physics to make sure we understand this. And that's really the effort here. But we shall. But despite the fact that there is no Earth planet, there is another fact which is obvious. There is a massive number of planets that are different, and that is a reality. So whether we like it or not, there is more than the majority of the star right now that we know they don't have a configuration like our solar system. So we already know we have been pushed back aside. We're not the only way to make a planetary system. We're just one amongst many. Whether it's 1% or 10% or 0.1%, I don't know. But we will find out. And it's a matter of maybe 20 years to find this out.
All right, that's good to know. So on a somewhat related question, so okay. Yep, okay. So this one. Okay, what makes it so difficult to detect small and light planets with long periods? So that part of the graph where it's empty, yeah.
Well, you know, it's interesting. Before we started finding planets, there has been a couple of papers produced that was essentially describing the fact that there's certainly two techniques that should not be used to detect planet. One of them is transiting, and the other one is radial velocity, which is the two techniques that are producing this gap right now. The reason for that is because they are poorly efficient to detect long period system. The transit, it's a matter of statistics. I mean, the chance to get a transiting configuration when you're farther out decrease. So you will have to observe a lot of stars, having each of them planets to get at least one or two transit out. So that's why the transit is the least efficient technique for that. Now, a small planet or light planet, by design, because it's small and light, will be difficult because the effect of that planet on the star, because we're looking at the star, will be marginal and within the noise or the structure of a stellar spot. So this is just a practical limitation. That's why people dream about other technology like direct imaging or more global motion discovery like astrometry, but still, you still are facing other problems. So what, on one hand, you lose on one, you will get other issue on the other one. So it's still, anyway, a planet is very common, but you have to remember, Jupiter is 1,000 times less mass than the Sun. And the Earth is even 300 times less massive than Jupiter. So it makes us very small in terms of mass. And the size of Jupiter is 10% of the Sun, and we, Earth, have 10% of Jupiter. So we're talking about a 1% size difference compared to the Sun. So imagine this is the Sun, you take 1%, which is maybe 2 fingers, so it's the size of the Earth. In terms of mass, there is a difference of 300,000, which is huge. So it's completely insignificant in terms of astrophysical element, but is so significant in terms of space or place when you can develop life. This is why people are so fascinated by the planet, because you need a planet to develop life.
So the long period also means that the transit, I mean, it's harder to catch it because it takes a long time to come back.
It's just the likelihood that you will be strictly aligned. So the longer is because the orbit can be in any direction. So it's like you want to aim at a target with an arrow. If you're very far away, the chance to aim at the center will be, if you go random, will be very little. So it's just the probability of happening, having a transit.
Right.
In addition to that, it's less frequent, so you have less data. You have everything is playing against you.
Right. Okay. Okay. So next question we have here. Okay. Okay. So maybe this one. Do you think that during the formation of the planet, the gases necessary for life escape due to insufficient gravitational pull of the planet?
Oh yeah, plenty. I think we don't have any more helium and hydrogen on Earth, and we have to make it. If you want to make it, you just leave. Mars suffered this. Mars has a very similar atmosphere than the Earth, we believe, early on, for 1 billion years about. But because the gravity is not enough, all this, gently went away. And this is why there is almost no pressure right now on the surface of Mars, and you cannot have liquid water on the surface. It just vaporizes right away. So yeah, of course, you need a minimum mass to maintain to maintain the atmosphere, to glue, the molecules, the heavy molecule glue to the planet. But some, they will escape anyway.
Okay. So another very interesting question. Can we predict how Earth will die? And how are all Earth-like planets elsewhere like?
Well, Earth doesn't really die. Earth is not alive. So, die is more something you would use for something alive, I would say. You can predict what is the future of Earth as a planet. Well, not much will happen until the sun will reach the end of this burning phase for the hydrogen. So at some point, lacking hydrogen at the core of the sun will force the sun to expand, and it will go into a phase that we call expanding phase and red giant phase that would engulf all the planet, at least up to the Earth. So the Earth will be engulfed into the sun, and at that point will likely to be vaporized entirely, and that's it. It's in 4 billion years, so I think we have way more to worry before that time.
Well, yeah, it will be long gone.
Well, just remember, our species has barely 1 million years, so I think we are just insignificant on that time scale.
Okay, we have time for just maybe one last question, which is, okay, so would it be possible for mankind to live in Mars or any other planets in the future?
Well, I think this is kind of this. It's kind of very popular these days to have these discussions. So my take on that is very simple. If you leave Earth, you die. You die because as a species, we're not designed for that. We have evolved with this planet. We're designed to survive on this planet, and not everywhere. If you go into the oceans, you die because you don't have the right element to survive. So we are very fitted for this planet for good reason, because we are the outcome of a very long evolution. So if you bring humankind on Mars, you die. Well, what you could do is you can trick and then create a new species. So it's certainly we can do right now. I think potentially we have tools to do that. We can maybe genetically modify ourselves. I think the scorpions are better resisting to the radioactivity. So maybe we can create a mixture between scorpions and humans that will be able to go Mars.
Scorpion man.
We can certainly imagine developing, but that's not us in terms of species. I think in terms of species, it's all the concept of our own evolution. So should we then thinking about the evolution of our own species and selective evolution of our species? So it's a very fascinating question right now. This is real. We have this potential. Tomorrow, a lot of people are now working on the origin of life. They may be doing from the lab what has happened early on Earth. It happened on Earth. There has been some chemistry going on there. It's just find the right recipes, and you create life in the lab. So you can imagine you create something alive that you can combine with the own species, and this has happened for almost 3 billion years, more than 3 billion years. This evolution of life, optimization of it. So I'm not a great fan of Mars. I think certainly spending resources to go to Mars, scientifically speaking, is interesting, but the idea you will create cities on this, I think it's just ridiculous. We should just spend the money where we need it, which is on Earth right now, and fixing the system on Earth. There's a lot to do, I can tell you.
For those of you who have more questions, I think you can engage Professor Queloz after this session, and feel free to ask him questions, I guess, right? Yeah. Okay, thank you very much once again for being here.
Thank you.
Thank you very much, Professor Queloz, and thank you, Prof Tan. Thank you for the very invigorating discussion.